Doctor, can you record the session, please?
Sorry?
Can you record the session?
Yeah, started. Okay. So on the slide here, you see some statements. These statements are related to the travel time studies topic, all of them. So now all of them are wrong. All these statements are wrong. This is what I'm telling you from the start. What you have to do is we'll go statement by statement and you will give me the correct statement. Okay, you find out the mistake with the statement and rewrite it in the correct form. Okay, this is what you have to do. So, for example, the first statement, travel time studies should be done over a length of less than 1000 feet. So, what's the problem with this statement and what's the correct form of this statement? Yes, please go ahead. Travel time studies should be done over a length of less than 1000 feet. The statement is not correct, but you have to identify the mistake and rewrite it. Yeah, anyone? And by the way, if you don't attempt a statement, I'll just move over. Okay. So anyone? Sadiq, Haya. Travel time studies should be done over a length of less than 1000 feet. What's the problem with this statement? How we can correct it? Okay. Okay. Can you give me the correct word here? And by the way, you can open your notes. You can keep the slides in front of you or your own notes from the last lectures in front of you. So it may be more helpful. Okay. Open your slides or notes, make more helpful. So Mariam is saying, okay, I will accept it. Not less than 1000 feet. The correct word was significant length of the highway or route. Okay, so in the first statement, this should be replaced. This should be replaced. Okay, and then you write over a significant length of the highway or route. Okay, this is what is given in the book, but okay, not less than 1000 feet, I will still accept it. Okay, or there's another variation. There's another correction which you can do this with this statement. It will become true. Keep it as it is. Keep this as it is, and instead of travel time, you write spot speed. Okay, so that statement will also become true. So instead of travel time studies, if I write spot speed studies should be done over a length of less than 1000 feet, this is also correct. Okay, so either replace the end or replace the start, you will get the correct statement. Okay, moving on. Floating car technique is applied on multi-lane highways to find out maximum speed. Floating car technique is applied on multi-lane highways to find out the maximum speed. How we can correct it? Yeah, significant length. Yes, Mariam. Very good. 2-lane highway. Okay. It is applied on 2-lane highways. Okay. Anyone else wants to add something here or give me some other correction? So she is correct. This should be replaced with 2-lane, not multi-lane, 2-lane. Any other variation possible? Or any other additional correction to this statement? Can you think of that? Anyone? Zahra? Haya? Ali? Okay. So another correction, if you want to keep again the start same, if you want to just keep it floating car, okay, then it should be 2-lane, and then this is not maximum car. This is not maximum speed. It will be average speed. Okay, floating car is not for maximum speed, because in floating car you are not asking the drivers to overtake everybody. Okay, so that is for average speed. So floating car is for 2-lane highways and for average speed. Okay, so there are two corrections in this system. Or instead of making these two corrections, you can do one more thing, which is keep the statement as it is. Just change this thing. Instead of floating car, it should be what? Can someone tell me, if I keep this as it is, then what should be this? What should be the name of the technique then? Or if I ask you which technique is used on multi-lane highways to find out maximum speed, what is the name of that technique? Anyone? Raneem, Mahmood. What is the name of the technique which is used for finding out maximum speed on multi-lane highways? No. I am asking about the name of the technique, not the name of the speed. Name of the technique. Which technique is used for finding out maximum speed on multi-lane highways? Okay, I'll move on. You can see which one is it from the notes. Okay. Statement number 3. License plate technique of travel time study requires cars, drivers, observers, and stopwatches. How can I correct this statement? License plate technique requires cars, drivers, observers, and stopwatches. Yes, Mariam, you are right. Yeah, maximum car technique is used for multi-lane highways to find out the maximum speed. Yes, you're right. Well done. Okay, now statement number 3. Statement number 3. License plate technique requires cars, drivers, observers, and stopwatches. Correct this one now. Yes, anyone? Sadiq, Ali. License plate technique requires cars, drivers, observers, and stopwatches. Anyone wants to correct it? Yes, yes. It only requires observers at start and entry point with a pen and paper. Okay, that's it. Okay, and again, another variation in this statement can be you keep the remaining part of the statement as it is, but instead of license plate, you say test car. A test car technique requires all these things, not license plate technique. Okay, so either you keep again license plate technique requires and then 2 observers. Okay, or you can write test car technique requires cars, drivers, observers, and stopwatches. Okay. Fourth statement: a driver and observer must be present in every test car. What about this statement? Okay, the key word here is must be. A driver and observer must be present in every test car. Must not. Then how would you get the observation, Mariam? Or anyone else? If you don't have a driver and observer, how would you get the observation? You don't need a driver in the car. How will the car drive? If you don't have a driver, how will the car drive? I don't know what you mean, but yeah, we need a driver. Driver is necessary. Okay, an observer may not be there, and why? Again, you need to go back and check the notes. Okay. Okay, moving on. Delay equals average travel time minus maximum travel time. Can you correct this statement? Delay equals average travel time minus maximum travel time. What's the problem with this statement? Delay equals average travel time minus maximum travel time. Anyone? Raneem? Mahmoud? Maram? The statement says delay equals average travel time minus maximum travel time. No. Delay is travel time minus running time. That's it. Delay is travel time minus running time. It doesn't have anything to do with the maximum. Delay is average travel time minus maximum. Oh, sorry. Average travel time minus average running time. That's it. Okay. Next statement, if true mean is given, then standard error or E value is assumed to be 1. If you have true mean, then a standard error, which is denoted by E, is assumed to be 1. Who can correct this statement? If you have true mean, then standard error represented with E is assumed to be 1. Who can correct this statement? Yes, assumed to be equal to standard deviation. Yes, Zara, very good, correct, well done. If true mean is given, then E is assumed to be equal to standard deviation. We did it in an example in the last lecture. Good, well done, Zara. Okay, frequency distribution is always represented as a curve. Frequency distribution is always represented as a curve. Who can correct this statement? Is it necessary that frequency distribution must always be represented as a curve? What do you mean by frequencies? Raneem? Can be represented as frequencies meaning what? No, I'm talking about figure, a graph. A graph. So frequency distribution must always be represented with a graph or a bar graph. Good. Histogram, bar diagram. Good. Good. Yes, Mariam, line close to the point is also a curve. Okay, it's also a curve. So Raneem, you are correct. It can be a bar graph or a histogram, which I showed you again in the last problem. It can be a bar diagram. Okay, good. Well done. Average delay can be calculated as summation of probabilities of its occurrence. Okay, let me show you the problem in which we did it so that it will be easier for you to answer. If you remember in this example, the statement is related to this example. Okay, and the statement is saying the probabilities of delay are given in the second column. So if I add all the probabilities, if I add the values of this column, it will give me average delay. This is what the statement is saying. That if you want the average delay, just add the probability or chances of different delays. different values of the digits. Just add all these values and you will get the average delay. So who can correct this statement? Again, showing the statement. Average delay can be calculated as summation of probabilities of its occurrence. Come here. This is the summation. This is the probability of 0 delay and 40 seconds of delay and 80 seconds of delay. This statement is saying just sum these values and that's it. And it will give you the average delay. What is the problem with this statement and how we can correct it? Yes, anyone? No, not average. If you remember what we did in this example, I took the product of the two numbers and then I added them. So if you just add all the probabilities, it will always give you 1. Probability means a percentage, right? So if you add all the percentages, you will always get 1. Okay, so what we did in this example, I multiplied the probability with the duration. So 0.569 into 0, 0.3 into 40, 0.131 into 80, and then I added them. So if you just add this column, you will always get 1. Okay, so the correct statement would be average delay is a product of it's a summation of the product of probability with the duration of delay. This is the correct statement. Okay, that's a summation of not only probability but product of probability and the duration of delay. Okay, and this is what we did in this example as well. Yes, Zara, good. This is what I was saying. Required number of samples increase with acceptable error. This is very easy. Required number of samples increase with the acceptable error. Is it true or not? Oh, sorry, it's not true, but what is the correct statement? Required number of samples increase with acceptable error. Decrease, yeah. Okay, when you increase the error, when you are accepting more error, you need less samples. Okay, Haya, well done. Last one. Again, very easy. Travel time contour map shows the lines joining the segments of same elevation from a reference point. Travel time contour map shows the lines joining segments of same elevation from a reference point. Okay, tell me. Same travel duration, travel time. Yeah, good. Prani, very good. Again, two possibilities. Either keep the statement as it is and change elevation with travel time. So travel time contour map shows the line joining segments of same travel time from a reference point. Okay. Another variation, keep the statement as it is, keep elevation as it is, and remove the travel time from here because we already know that travel time can also be plotted for surveying. Okay, so maybe I'm talking about surveying contour map. Okay, so if you remove the travel time from the start of the statement becomes correct again. Or keep the start as it is, remove elevation and replace it with travel time. Okay, so these are the possible variations. Now whatever we have done in the travel time, same travel time, yeah, good. So whatever we have done in the travel time topic is, is just now reviewed. Okay, so I can move forward now. So last time I showed you travel time contour map, right, which is plotted for the travel time of the entire region. Another way of representing the travel time data is in a time distance diagram. Time distance diagram, which you can see in the slide here. Distance on the x-axis, time on the y-axis. Distance x-axis, time y-axis. Okay, so on the x-axis, so you see in this graph there's a solid line here. Okay, so this solid line is basically representing the movement of the car. So at 0 time, the car was at 0 feet. At 30 seconds, the car was at this distance. At 1 minute, the car was at this distance, and so on and so forth. Okay, so you note down the distance and the time, and you plot it, and you plot the movement of the car. Okay, then you see another line, which is a dotted line, and this has to be for a particular route. Okay, this is not for a region, this is for a particular route. Okay, so from one point to another point, that's it. Now you see a dotted line here, and on the dotted line you see that this dotted line represents average speed. Okay, how first of all, how do I calculate the average speed? Average speed is total distance upon total travel time. Total distance upon total travel time. So total distance is how much? 1400 feet. Total time is how much? 6 minutes. So 1400 divided by 6 converted to miles per hour will give you average speed. Okay, so average speed means total distance upon total time. Okay. Now this is a time distance diagram. This is a time distance diagram, right? And speed is not here. There is no access for speed here, right? So speed for this diagram means what? How do I represent the speed in this diagram? One axis is for distance, the other axis is for time. Where do I put the speed here? Or how do I represent this? Slope. Good. Good. Well done. Yeah, slope. Well done. So actually it will be the inverse of slope. Speed will be the inverse of slope because it will be y upon x, and on y I have time. Okay, so speed will be the inverse of slope. So first of all, find the slope. Okay, and then take the inverse. That will give you the slope of a line on this graph. Inverse of speed will give you the slope of a line on this graph, or vice versa. Inverse of slope will give you the speed of the line or of the car. Okay, so what did they do? They find out the average speed. They find out the average speed. Okay, and then whatever average speed they got, they took its inverse. So the average speed of 24.5. Then they took the inverse of 24.5, and using that value, the inverse value, they plotted a line from 0. So the inverse of this value became the slope of this line, the angle or the slope, whatever you want to call it. Okay, so first of all, they found the average speed, total distance upon total time. Then they did the inverse. Inverse became the slope of a line, and then they plotted the line equal to that slope from 0 onwards. Okay, so obviously this line is a straight line, no variation in this line because start to end there's one slope. Now if you look at the line which is for the car itself, the actual car which was moving from 0 to 1400, you see there's a variation in different segments. In different segments, the car is moving differently. The one variation which I want to talk about is the vertical line. So when the graph shows a vertical line, a time space diagram, time distance diagram shows a vertical line, it means what? What happened with the car? What is happening with the car here when the graph goes vertical? Who will tell me? The car stops. Well done. Stop. Yes. Hashim running. Well done. It stopped. Okay. So the stop delay is shown with a vertical line. So if you measure the height of the vertical line, it will give you the time of the stop delay. Okay. So time is passing, distance is not passing. Okay. And similarly, when the slope changes, that means the speed of the car is changing. Okay. So if you want the speed of the car in a particular segment, take the slope of the line and then do the inverse, you will get the speed of the car in that segment. So a time space diagram or a time distance diagram can help you find out these things. Another form of using the travel time data is to plot speed on the y-axis and distance on the x-axis. Speed on the y-axis, distance on the x-axis. Now this can help you to find out the effectiveness of different measures or different improvements on the road. If you have made any improvement on the road, whether they're effective or not, it can be judged using a speed and distance diagram. Okay, so you did a travel time study. Using travel time study, you calculated the speed and then you plotted the speed versus distance. Distance meaning the segments. So in this graph, you see 3 lines. There's a dotted line going from start to end, which they are saying before HOV. Then there's a dotted line, which is a smaller one, which they are saying HOV lane. And then there's a solid line, which is a mixed flow. Okay. First of all, what HOV means? HOV means high occupancy Okay, HOV means high occupancy vehicle. All buses are high occupancy vehicles. If a car is full of passengers, it is also a high occupancy vehicle. If a car is only carrying a driver, that is not a high occupancy vehicle. Okay, so high occupancy vehicle means a car or a vehicle which is carrying more passengers. Okay, so in some countries they have adopted HOV lanes. So they have a separate lane wherein the vehicles having high occupancy can go from. So that lane will have very few vehicles, so the speed of that lane will be higher, because not all vehicles are high occupancy, right? So you are providing a faster lane for which drivers? Drivers which are carrying more passengers. Okay, so people are encouraged to use a single car people are encouraged to use a single car for multiple passengers, or they will be encouraged to use the buses. Okay, so if you see the dotted line, the longer dotted line, it is clearly showing then when there was no HOV lane, the speed was lower. Okay, when HOV lane was established, the speed of the HOV lane was higher because obviously there is less flow, and the other lanes which were having mixed flow meaning everybody is going from there, high occupancy, low occupancy. So even in those lanes, the speed became higher. Why? Because some of the people who are going from this mixed lane, they shifted to the HOV lane. So the flow in the other lanes also decreased because of the HOV lane. Okay, so the speed of the HOV lane itself is higher, very high, and the speed of the other lanes also improved. It did not become as high as the HOV lane, but it also improved. Okay, so this is a way. So you can clearly see the effect of the HOV lane increasing the speed through this diagram. Another diagram, the only difference between this one and the last one is there is no before HOV lane data, so you only see two lines. Okay, so what is this showing? That HOV lane has higher speed than the other lanes. The other lanes which have mixed flow, their speed is lower than the HOV lane. Okay, so HOV lane is providing an incentive for the drivers to carry more passengers with them. Okay, so apart from the discussion of the HOV lane, the main point here is that the travel time study was used to calculate the speed of different segments, and then they are plotted, and then you can see the effectiveness of different measures on the road. Okay. Now we come towards the topic of intersection delay studies. Now, intersection are unique points on the highways. Why they are unique? Because on intersections, the flow of vehicles is stopped. So you cannot use volume or flow or speed or density to find out the quality of traffic on the highway. Okay, or quality of traffic flow on the intersection. Okay. On an intersection, since the roads are intersecting, everybody has to slow down or stop. So if you are trying to measure the effectiveness of intersection using speed or flow, it will always be very low. Okay, it will always fail in that regard. But if you go for delay studies, then we can measure the effectiveness of the devices which are using at the intersection. Okay, so effectiveness of intersections is measured in terms of delay. An intersection which causes more delay is less efficient as compared to intersection which causes less delay. Okay, and so on and so forth. So higher delay means less effectiveness, lower delay means higher effectiveness of the intersection. Now wherever you have an intersection, we have a control device as well to regulate the flow of vehicles. So what are these control devices? A signal is a control device. A roundabout is a control device. A stop sign is a control device. So intersections normally have control devices to regulate the flow. Otherwise, if the drivers are left to their judgment, there will be accidents. So the delay which is measured on the intersection is known as control delay. What is control delay? It is the delay which is measured at the intersection. Okay, and that is the delay caused by the control device which you are using at the intersection. Control delay comprises of three things. There are three components or three parts of control delay. First, time in queue delay. So when you reach the intersection, the signal was red, you had to wait on the near the stop line. That is your time in queue delay. When you cross the stop line, time in queue delay ended. Okay, or you came to the intersection, there were already three cars in front of you, you waited behind these cars. Okay, so that is your time in queue delay, and until you cross the stop line, the time in delay, the time in queue delay will be counted. Okay, so time in queue delay is counted from the point of time when you join the queue till you cross the stop line. That is all is considered as time in queue delay. Okay, so this is one part of control delay. Another part of control delay is a deceleration before you join the queue. So before you come to the stop line or before you join the other cars, you have to decrease your speed, otherwise you will not be able to stop, you will have an accident. So this deceleration is part of control delay. When you cross the stop line, you have cleared the intersection now. So now you will try to accelerate. There is no barrier in front of you, there is no restriction for you, no signal and nothing for you. So you will try to accelerate. So this acceleration is also part of control delay, because if there was no intersection, you would not have to decrease your speed. So you did not have to increase your speed as well in the end. Okay, so deceleration, then joining the queue or time spent in the queue, plus acceleration back to your original speed or to the speed of your choice. All these are part of control delay. Deceleration, time in queue, plus acceleration. All these are parts of control delay. The measurement of control delay depends upon the type of control device you have. If you have a signal, that is different. If you have a roundabout, it is different. For a stop sign, I have not seen any stepwise method for measuring the delay on a stop sign, but there are softwares available. You can use the softwares to find out the delay. So I will discuss in this class methods for delay measurement for two types of control devices, signals and roundabouts. And I will start with signals. Okay, I will start with a signal. So the method of delay measurement on a signal is given in Highway Capacity Manual of 2000. Highway Capacity Manual of 2000. It has not been changed since then. The procedure is the same. In this method, you need two observers on the signalized intersection. Two observers. And this method is only applied when you have undersaturated conditions. Undersaturated conditions. Now, can someone tell me the meaning of saturated? Saturated means what? If I say this thing is saturated or this cup is saturated, what does it mean? Okay, saturated means what? Capacity, right? Yeah, right, like to the maximum limit, right? I will take the word from Mahmoud, the capacity. Okay, so the capacity of absorption. Okay, you don't have to delete. Okay, don't have to delete. Just keep it. What's the problem? Okay. So if you are talking about saturation in terms of moisture absorption, so maximum moisture absorption is saturation. If you are talking about in terms of density, so maximum density is saturation. Okay, so anything up to the capacity is saturation. Anything up to the capacity is saturation. So the method which I will explain now is for undersaturated conditions. So the signalized intersection must be undersaturated. Okay, saturation is capacity, overcapacity is oversaturation, undercapacity is undersaturation. How do I know signal is undersaturated? So there are two conditions to know that. Okay, if you fulfill any of these two conditions, that means signal is not undersaturated. First of all, keep this in mind. If you want to know a highway is undersaturated or oversaturated, it's very easy. If there's a traffic jam, if there's a queue of cars are stopped on the segment, that is oversaturated, traffic jam. Okay, but for signals, it is very difficult to apply this criteria, right? Because on a signal, after every few seconds, the car has to stop. Okay, so having a queue of cars is not the indication the signal is under or oversaturated. Okay, because the cars are stopping because of the signal, not because of traffic jam. Okay, so to know whether we have undersaturated or oversaturated conditions, first of all, you will look at how many cars are stopped. Not whether the cars are stopped or not. How many cars are stopped because of the signal? If that number is less than 20, then we consider it to be undersaturated. The cars which are stopped in the queue on a signal, if they are less than 20, you can consider it to be undersaturated. The second condition is, for undersaturation, the second condition is that no car is waiting on a red phase from the previous red phase. They call it overflow. Overflow. Okay, so overflow means what? A car has to wait for more than one red phase for their turn to clear the intersection. So you came to the intersection, there was a very long queue, so you stopped behind so many cars and you were wondering where is the signal, I cannot even see it, what will happen to me? Okay, and the signal becomes green, you take a sigh of relief and you start moving, but the driver in front of you is in no hurry. You know, he's playing with a mobile, or he doesn't have anything else to do in his life, so he's moving slowly, or because of any other reason. Okay, because of the long queue, when you reach close to the stop line, the signal becomes red again. Okay, so that is overflow, because you waited for more than one red phase to clear the intersection. That is overflow. Okay, so if you see cars which are in the queue, they cannot pass the stop line in one green phase, that means this is oversaturated conditions. Okay, so the queue must be less than 20 vehicles, and the other is all cars which come during one red phase move during the next green phase. They clear the intersection during the next green phase. Okay, so these are the two conditions. If you meet any of these conditions, then the signal is, if you don't meet any of these conditions, the signal is oversaturated. Okay, the queue is longer, the cars are waiting for more than one red phase, the signal is oversaturated. Don't apply that procedure, the procedure which I'm about to explain. Don't apply this procedure to find out the delay in these conditions. Okay, another thing which you have to find out is the free flow speed of the highway which is coming towards the intersection, the free flow speed of the highway. Now the problem is, or you may argue with me, I just told you we should not measure the speed of the cars on the intersection because they are supposed to stop or slow down. So how would I get the free flow speed for the intersection? The answer is, there are two answers. There are two possible answers. The first answer is, I don't need the free flow speed of the intersection. I need the speed of the highway which is coming towards the intersection. So you go behind the intersection on the same highway and measure the speed at a spot where there is no effect of the queue or the intersection. So for example, the queue is normally 100 feet behind the intersection. So you go maybe 300-400 feet behind that point where the queue normally comes, or till the point where the queue normally extends. You go further behind that point and find out the free flow speed. Okay, behind the point where queue normally comes to. Okay, so this is one way of doing it. Find a spot which is not affected by the signal or the intersection. So it is so behind the intersection, there is no effect of intersection on that car which is in that spot. This is one way of finding out the free flow speed. Another way of finding out the free flow speed is only measure the speed of the vehicles which are crossing the intersection, which are coming to the intersection and crossing it during green time. Only measure the speed of the vehicles which come and pass the intersection during green time. Okay, so you came to the intersection, you already saw the signal was green. Okay, and then it's a matter of life and death, right? I cannot slow down, I cannot stop, otherwise I have to stop on the red signal. Okay, and if I'm coming towards the signal, it's in green, and I let it turn red, okay, that's an insult, right? That's an insult to my driving. How can I let that happen? So at that time, I will become, I don't know, the old guy was Michael Schumacher. I don't know who's the new champion now, but I become that champion of car racing at that time, and I will try to go as fast as possible so the signal doesn't become green. Oh, sorry, the signal doesn't become red. Okay. So stand on the intersection, measure the speed on the intersection, but not for all the cars, only for cars which come during the green and they immediately cross. Okay, so the speed of those cars can also be considered close to the free flow speed. Okay, so these are two methods by which you can find out the free flow speed. Now, so I said we need two observers. What these two observers are doing, observer 1 is taking or counting the number of vehicles in the queue on the intersection after a specified period of time. So to observer 1, you give him a specified period of time. Okay, 10 seconds, 15 seconds, 20 seconds. And you tell him after that much time, count the number of vehicles in the queue and record it. So I will count it now. He will count it maybe after 10 seconds, then 20 seconds, then 30 seconds, and so on. Okay. So he is counting number of vehicles in the queue. Now, how much time interval should I give him? Should I give him 10 seconds, 20 seconds, 30 seconds? How much time interval should I give him? After which he will recount the number of vehicles in the queue. The time period depends upon the signal cycle. What is a signal cycle? A signal cycle is the time during which signal completes all its indications. Signal completes all its indications. So in some countries, the indications include red, yellow, red, green, and yellow. That's it. In our cases, we have two yellows, right? So in our case, a signal cycle will be red, yellow, green, and then yellow. Okay. So from a start of one red to the end of the second yellow. This is one cycle for us. In countries, other countries, it will be a start of one red to the end of yellow, the only yellow they have. Okay, so this is one cycle when the signal completes all its indications. Now, the time period which you are giving to observer 1 should be integral divisor of cycle length. Integral divisor of cycle length. Now, I will not explain integral divisor. I will explain you the inverse of integral divisor, which is multiple. Multiple. Integral divisor is the inverse of multiple. Okay, so for example, if I say 2, it can also be when the queue growth is higher than the flow rate. Yes, it will happen when the flow rate is if the queue growth is higher than the flow rate, you will see the overflow in that case. Okay, so it is included. It is included. Okay, what you are saying is already included in the conditions. Okay, so if I say 2, the multiple of 2 is what? 4, 6, 8, 10, all of them are what? Multiple of 2. Okay, so 2 is what? For 10, 2 is what? Integral divisor. Okay, 10 is a multiple of 2, so 2 is the integral divisor of 10. Okay, so now I think you get the idea now. 2 is an integral divisor of 10 because 10 is a multiple of 2. Okay, so they are related to each other. So for example, let's say your cycle length is 60 seconds. Okay, so if I give a time interval of 10 seconds to the first observer, so 10 upon 60 upon 10 is 6. Allowed, no problem. Somebody else comes and says make it 12 interval, 12 seconds interval. So 60 upon 12 equals to 5, no problem. Again, integer, integral divisor. Somebody else comes and says make it 11. Now 60 upon 11 is not an integer. Okay, so this cannot happen. This is not allowed. Okay, so the time interval which you are giving to the observer 1 must be integral divisor of the cycle length, or cycle length must be a multiple of the interval. Okay, now this observer is counting vehicles in the queue. Okay, now queue can be stopped or queue can be moving. Queue can be stopped or queue can be moving. Okay, now forgive me for taking some extra time. We finished the activity which I gave you the start quickly in the previous session, so I was able to cover more content there. You guys took more time. Anyways, I just take a couple of more minutes. If you want to leave, you can leave. You can see it in the recording later on. Okay, but I have to finish it. So a queue can be stopped or queue can be moving. Stop, you know, stop, right? Queue, you are still in the queue if you have not crossed the stop line or if you have not reached the other side. A car which has joined in the queue, okay, the car stopped or the car joined the queue, that car, even if it is moving, it will be considered part of the queue if it has not crossed the stop line or reached the other side. Okay, if a car is going through means straight. So if a car is going straight, until it crosses the stop line, it is considered part of the queue. Okay, and if a car is turning, so it is turning towards the side. So until it reaches the other side, it will be considered part of the queue. Okay, so on this side there may be a stop line or there may be a pedestrian crossing. So until the turning car crosses the pedestrian crossing or the stop line, it will be considered part of the queue. Or if you are considering a straight car, a straight movement car, through movement, then when it crosses the stop line, you will consider it to be to have left the queue. So until the straight car crosses the stop line or until a turning car reaches the other side, they are considered part of the queue. So until this happens, you will keep on counting them in the queue. Okay. Second thing you have to consider is the survey should continue until all the cars which came during your survey period have left. Okay, so for example, when you are about to finish your survey, somebody told you do it for 15 minutes. At the end of 15 minutes, there are 2 cars still in the queue. These 2 cars came during your period, your survey period. So you must take extra observations until these 2 cars leave. Okay, so observer 1 should take extra observations until the queue becomes 0. The queue of the vehicles which came during his time interval. Okay, all vehicles which came during his time interval, during his period of observation, until they have left, he will keep on counting the cars in the queue. He will keep on taking observations. Observer 2, what is observer 2 doing? Observer 2 is recording 2 things. How many cars came to the intersection? How many of them stopped? So he's taking 2 records, 2 observations, 2 types of observations. Number of cars came to the intersection, number of cars stopped at the intersection. So number of cars arrived and number of cars stopped. They can either be equal if everybody has to stop, or it can be number of cars stopped may be less than number of cars arrived. If everybody did not have to stop, the number of cars arrived will be more, number of cars stopped will be less. But for observer 2, there is no interval. You will just keep on counting them until the time is finished. You start from the first second till the last second. You just keep on continuously counting it. There's no time period for it. No cycles, no time period. Okay, continuously. After you take the observations, what should you do? You will apply a series of equations to find out the total control delay. The first equation is for time in queue delay, TQ. So you need IS. IS is the interval you gave to observer 1. So you gave him 10 seconds. After every 10 seconds, count the number of vehicles in the queue. That is IS. VT coming from observer 2. Total number of vehicles arrived at the intersection. So this will come from observer 2. VIQ, the number of vehicles observer 1 counted every time. So then he will give you multiple observations. You do the summation for all the observations. And 0.9 is the constant. It will not change. Then you will calculate VSLC. Vehicles stopped per lane per cycle. So vehicles stopped will come from observer 2. You have to count number of lanes, and then you also have to count how many cycles the signal finished during your time period. Okay. Then we need FVS, fraction of vehicles stopped out of total. How many stopped? So V stop upon VT. Then D is the total delay, total control delay. So you need TQ, FVS. You already calculate these things, and you need the correction factor. Correction factor will come from this table. So for using this table, I need free flow speed and I need VSLC. So for example, your free flow speed is 40. So you will find it in this row. And your VSLC is 10 vehicles. So you find it in this column. So your correction factor will be +4. So you multiply this in this equation. Okay. This is a sheet for data collection for observer 1. Observer 1. Although you see VT and E stop here as well, observer 2 will put these things after the survey is finished. Okay, so observer 2 is recording it somewhere else, and then he will put it in this sheet. So then we have some general information: who is doing the survey, when and where. Okay, name of the intersection, area, year, number of lanes, you will count it, the interval you have given to observer 1, integral divisor of the cycle length, 2 values coming from observer 2 at the end, and cycle length of the signal. You must know it before you start the survey. Then you will write the clock time in this column, what time you started the survey, cycle number. Okay, first cycle, second cycle, third, fourth. So it's like a serial number. Okay, and in each cycle you will have multiple observations of the queue length, because in each cycle you may have 2 or 3 intervals. So for example, cycle length is 60 seconds and your interval is 10 seconds. So in one cycle you can have 6 observations of the number of vehicles in the queue. Okay, so again, it can be more as well. 10 is not the maximum number. It can have 12, 13, 14, whatever. So it's not fixed. So once you complete one cycle, then you start the observations, recording the observation in the new row. Okay, so each row is for a new cycle. So whenever the cycle completes, you will go to the new row, put the time again, put the cycle number again, and then you will write the observations. Okay, so in the next class, inshallah, I will show you an example how the numbers are recorded and how they are calculated. If you have any questions, please go ahead, let me know. Any questions, queries? Others can leave. Yeah, sure. Others can leave. Any questions, queries, any problems? Please go ahead. Okay, thank you for listening and participating. Sorry for taking extra time. All the best for the exam. Some of you had exam. Okay, so, or have exam. So all the best for that. Okay, and see you on Sunday. Have a nice weekend. I hope you can enjoy it even after the exam. Okay. Assalamu alaikum.